So anyway, during lunch and tea break, we can still have time to communicate. Next, we would like to have Xiao Jun, founder and CEO of CloudNetEngine, to talk about next generation virtual switch. Good morning, everyone. My presentation is made in English.
I'm from CloudNetEngine. CloudNetEngine is a virtual networking startup, and mainly focus on virtual networking solutions. And virtual switch is one of our key focus. And
关注的核心领域。这是我今天将为大家介绍的主要内容。第一个部分呢，我们将会为大家介绍一下下一代虚拟交换机的核心性能，以及我们自己的一些展望和思考。然后接下来第二部分，我们将会深入的去分析一下 CloudNetEngine 的虚拟交换机。然后最后呢，也将会为大家做一个 Q&A。上一个环节大家问了很多好问题，我觉得大家一定是对虚拟交换机有了很深入的了解，所以说我觉得这是一个非常好的现象。下面让我们快速的来看一下目前为止主流的虚拟交换机，我们把它们按照工作负载进行了分类。在左边的这一栏，我左手边这一栏，大家右边的这一栏，这些呢是企业级的工作负载。企业级呢，我们是指传统的一些企业级应用，以及那些在公有云上运行的一些应用。在我下面是 NFV 类型的。作为 vSphere 来说，它能够获得行业的最大的支持，但是很多时候它并不能够支持 NFV 类型的工作负载。所以说，通过这个分类，大家可以了解一下，就不同类型的工作负载，它们需要使用哪种类型的不同的虚拟交换机技术。提到虚拟交换机的话，我们一直都要考虑到它的大背景。在过去的几年当中，我们一直都在谈软件定义网络的话题。软件定义网络 SDN 可能是最热议的一个论点。SDN 呢，应该是2010年就已经开始，同时呢，也是主要关注在企业级的工作负载应用。我们有很多的初创企业都是关注在 SDN 的开发之上，希望呢能够是解决控制面板的可扩展性问题，比如说 CloudNetEngine 也是被 VMware 在2012年收购。绝大多数的工程师在那个时候呢，都是软件工程师，而并不是网络工程师。这也就意味着数据通路的效率是很大程度上被忽视了。下面再介绍一下网络功能虚拟化。NFV 的话，它主要是关注在我们这种发夹结构的网络流量性能，可能就缩短延迟是我们最主要的一个要求。我们也是正在非常严谨的去考虑后续的解决方案。在 NFV 的应用环境之下，基本上所有的资源都是已经预先被分配好，我们可以非常好的对它进行使用。这也是一个非常典型的企业级工作负载。下面我将会为大家做更加详细的介绍。这个背景呢，我就简单的说一句。在任何的 IT 基础设施架构之下，我们都是为了为应用来去做基础的。所以说，我们不管做什么，都必须要以应用为导向。我们有很多新的类型的应用，不管是大数据、社交媒体，它都能够会产生大量的数据流。这也对 它的下层架构上带来很大的挑战。所以说，我们在过去一段时间，网络行业也正在不断经历变革，我们在虚拟交换机的行业也面临着很大的挑战。让我们退后一步，来去分析一下，在新时代、下一代虚拟交换机究竟有什么样的核心需求？这些主要的标准又有哪些？当然，第一个也是最关注的一个就是性能。我们必须要有非常高的性能，能够支持不同类型的虚拟化的工作负载，比如说是企业级的，还是其他低工作负载的情况。第二个，我们需要考虑就是 CPU 的能效。CPU 的能效也是性能的一部分，但是我们想单独把它拿出来强调一下，因为 CPU 的 efficiency 实在是太重要了。虚拟交换机它是在一个非常独特的物理位置上运行的，它也是必须要把计算资源与其他的虚拟机进行交换，在同一个主机上进行交换，这就意味着 CPU 的效率非常的关键。然后第三个就是丰富的功能性。我们的虚拟交换机必须可以同时支持公有云还有私有云的不同的用例。比如说，在性能的角度来看，以及功能性上，对于企业级的应用是非常关键的。最后一个也是我们需要关注的，那就是集成的简单性。集成它必须要做得更加的便捷。我们必须要让它能够在一个生态体系之下容易集成进去。像Jim一开始所说的，
大家好，因为这个 presentation 之前有些这个国外的 customer 他们要求有一个 English 的这个 presentation, so I will do it in English. Sorry about that. And so I'm from CloudNetEngine. CloudNetEngine is a virtual networking startup, and mainly focus on virtual networking solutions. And virtual switch is one of our key focus. And here's the agenda. In the first part, I'm going to initiate some thoughts on what kind of characteristic of the next generation virtual switch would be. And then I will deep dive on the CloudNetEngine virtual switch, and followed by a Q&A session. I heard quite a few very good questions on the last session, and so I guess you guys pretty much have a well understanding on virtual switch. So that's really good. And then let's take a quick look on the major virtual switch right now, and we categorize them by the workloads they supported. On the left-hand side, actually it's enterprise workloads. Here, enterprise, we mean the traditional enterprise application and also the application running inside of public clouds. And on the right-hand side is NFV type of workloads, as we know that mainly for telco. And as we can see that the vSphere probably get the best support from the industry, and but somehow you cannot really support NFV type workload. And so these slides essentially give you a sense that right now, for different kind of workloads, they're using different kind of virtual switch technologies. So when we talk about a virtual switch, we cannot really leave the context. I think over the last few years, SDN and NFV probably the most dominant context here. And as we know that SDN started from maybe 2010 and mainly focused on enterprise type of workloads. And quite a few startups focusing on decoupling the control plane and the forwarding plane, and try to solve the problem of control plane scalability. For instance, that when Nicira was acquired by VMware in 2012, most of the engineer in Nicira is just distributed system software engineer instead of networking engineer. So that means the data path performance or efficiency is really overlooked on that perspective. And for NFV, as we know that it's mainly focused on hairpin type of traffic. And the throughput and the latency is probably the dominant requirements. And the feature set, we know that is usually not seriously considered yet. And also, in NFV case, pretty much all of the resources just pre-allocated. And were used exclusively. That's very different from the typical enterprise workloads, as we'll see in next few slides. We can probably skip this quickly. And so essentially, we mean everything actually in IT infrastructure just supports applications. So everything is application driven. So as we can see, that there are a bunch of new type of application here, social, mobile, big data, and it's introduced a lot of east-south traffic and put a huge amount of challenges on the underneath networking infrastructure. And so there have a bunch of transformation in the networking industry and also a lot of challenges on virtual switch. So let's step back and really abstract those requirements. We think there are a few main requirements. And the first and the foremost, probably the performance, as we need to support variety of kind of workloads. For instance, the enterprise workload and NFV type of workloads. And the second one is CPU efficiency. This one pretty much is part of the performance, but we just highlight here is because it's super, super important. As we know that the virtual switch is essentially running in a very unique position since it needs to share the computing resource with other virtual machines on the same host. So the CPU efficiency is very critical in this case. And this third one would be the feature richness. And we need to have a virtual switch to really support both public cloud and private cloud use cases. For instance, right now, we know that OVS DPDK, for example, OVS DPDK probably mainly for performance, but really not for feature richness. So it's really hard to deploy for enterprise type of workload. The last but not least is ease of integration. So we have to live in an ecosystem. Like Jim mentioned, the project FD.io, that's pretty good, but comparing to OVS integration, I think OVS probably have some advantage in that regarding. Okay, so here's our source, actually. Let's take back to the major existing virtual switches. And what we are thinking is, there are quite a few very great technology on data paths, for instance, the DPDK, to help in the NFV type workloads. Why cannot we leverage those technologies to really also benefit the enterprise type of workloads? Why cannot we do that? On the other hand, there are a bunch of enterprise type of workloads have quite a few features. For instance, overlay. Definitely, it can also be used in NFV type of environments. For instance, overlay technology can help the service chaining a little bit. So what we are thinking is we need a unified solution. We don't necessarily to separate the enterprise and the NFV type of workloads. Here, the platform we just mentioned KVM, since we don't. vSphere probably they dominate hypervisor radar, but I don't think that really can support NFV type workloads if you take a deep technical insight. So in that, if that base is set, we essentially need a unified virtual switch with high performance for all of workloads and have a high efficiency to really support the enterprise use case and also have feature richness and the ease of integration. That's our goal. So that's our thoughts on this front. Okay, that's pretty quick. Go through some backgrounds and share a few visions from CloudNetEngine. Now I'm going to deep dive onto the on the CloudNetEngine virtual switch. So the first thing is that when we build a virtual switch, we need to really think about it in a holistic view. As we know that virtual switch probably using quite a few components, we cannot really just bring them together as is, as they have different kind of design philosophy in different components. So we need break the silos. That's the first thing. So take a concrete example here is that, for instance, in DPDK we host driver, when we enqueue or dequeue from a particular queue, we need using expensive atomic compare and set instruction to guarantee the integrity of a queue. But somehow in a virtual switch solution, the queue is already locked in the core logic. So it's really unnecessary to use those kind of expensive instructions. So that means that's what I mean. We need a holistic view to really streamline all of the critical data paths. Let's take a quick look on the integration story. Here, I don't know if you guys can see. Actually, the CloudNetEngine virtual switch at the bottom right side, there have a box. That's a CloudNetEngine virtual switch, and it's mainly have two components, two parts, and the gray box is, we call it the front end. We just reuse OVS, let's say OVS vSwitchD and OVS DB server, and it provides OpenFlow API and also OVS DB API. On the right side, in the blue box, is CDP. CDP means CloudNetEngine data path, and it provides ODP. Sorry about it. There's a bunch of terms, so that might be a little confused. The CDP means CloudNetEngine data path. It provides ODP API. ODP, if you guys have deep understanding on OVS, that stands for OVS Data Path API. So it provides crude operations for data paths, for ports, for flows, and also packet upcall and packet execution. So that's ODP interface. And also provide advanced API. Advanced API means the API CloudNetEngine virtual switch provided, but not included in the ODP API. So it shows the high-level architecture of the CloudNetEngine. In terms of the integration, as we know that pretty much we can have a 3 tiers architecture. On the top is CMS, OpenStack, CloudStack, etc. And in the middle there is SDN controllers, a bunch of SDN solutions over there. And in the bottom, that's for the engine. So let's take a quick look on the integration approaches. The first one would be, let's say, OpenStack, how OpenStack integrated with OVS. It's essentially bypass all of the SDN controller, just using OVS agent to directly talk to Neutron server. So in that case, the OVS agent can be reused, directly talk to OVS API or OVS command line, and that will eventually invoke some logic inside of CloudNetEngine data path. And the second approach, we just using OpenDaylight as an example. As we know that OpenDaylight sourceband, it can talk to OpenFlow API or OpenFlow API and OVSDB API. So in that regarding, its property is almost transparent to OpenDaylight solution, as we stick with OVS API. And the third approach is a little bit different. Here, we take a Metadata as an example. So in that case, the OVS interface can, we don't necessarily use OVS API. And the Metadata can directly invoke the ODP API and also advanced API in case it needs some advanced feature. So that's kind of the integration story for CloudNetEngine Virtual Switch. Okay, let's break down to more details. And this virtual switch architecture, and on the left side, the gray box we just mentioned, it's kind of CloudNetEngine front end. We just reuse OVS vSwitchD and OVSDB server. Here are some components with a star mark. It just means we take from open source, but with some kind of modification or enhancement. On the right side, that's the breakdown of CloudNetEngine Virtual Switch data path. So on the top layer, as we just mentioned, it's just API layer, and it exposes ODP APIs and advanced API. At the bottom, DPDK is essentially a foundation for our data path. And also, we rewrite the whole vhost, the VirtIO data path. That means the enqueue we just rewrite for some reasons, but we are seriously thinking how could we contribute back to the whole community. But as I just mentioned, we probably using different kind of philosophy, so that's going to take time. Another thing is about NetChain. NetChain is a very lightweight framework to plug in new features. We will see in next few slides. And in the middle, there's a bunch of modules. And from left to right, we have scheduler. Scheduler essentially schedule the receive queues across different polling threads. And adaptive polling, we will see that essentially it can enhance overall efficiency. And I also have some utilities for unbuff management and timer management. In the middle, there will have a classifier, flow cache, and the forward engine. That's pretty much the same as OVS DPDK stuff, but with some enhancements. Then we have MudQ, overlay support for VXLAN and GRE, and secure group, COS, offloading. This, I just heard quite a few interesting questions about the offloading. You can see we take a different approach than what we just mentioned. So that's probably what you wanted. And also sleeving, as someone asked, how could you really troubleshooting a networking problem? Okay, that's the overall architecture. In next few slides, I'm going to share a few experience that might help anyone who building application on top of DPDK. I think the first one is mbuff. Mbuff is significant in the whole DPDK library. And virtual switch is as a particular application on top of DPDK. There is some special things we need to really be care about. The first thing is about the metadata. As we know, the virtual switch using a bunch of metadata to help the switch forwarding or any other kind of features. So the reset of those dynamic fields of a particular mbuff is very significant. Take an example. There might be over 10 dynamic fields when you free mbuff. If you just reset those fields individually, that's going to waste quite a few times. So if you can really group those dynamic fields in one cache line or two, that will definitely help since we can using vectorize the reset. So that will be really helpful. Another thing is about the bulk memory free. So as we know that the mbuff free is most happen on the in-queue logic. So when you deliver the packet to the destination, you just try to free all of the packets. In that case, most of the packet coming from the same source port and most likely from the same memory pool. So we can actually batch those packets free instead of free them individually. That will help performance. And the third one is not essentially about the performance, but about the robustness. So as we know that mbuff is really, it's really easy to get wrong when you process mbuffs, and especially when you have many features, and you're using a lot of metadata. So one technique here we suggest is that you need to ensure the integrity of a single mbuff at any given time, which means that the metadata, the significant metadata, let's say number of segments, packet length or data length, and the next pointer must be consistent across the whole life cycle. So you can do a number of assertions in any critical packet processing logic to ensure that there is no anything wrong. So that's really helpful during our virtual switch development. And the next thing would be instruction per cycle. As we know that the instructions per cycle is have many impact on the overall performance. But how can we really achieve the better instructions per cycle? Here is our experience, and we should parallel any independent packet processing as possible as we can here. Processing means, parallel means that since a piece of code, if they are just dealing with independent data, so if we have such code, the compiler can really help to shuffling those data access, and they can boost the instruction throughput. So there have two concrete examples. One is that in virtual in-queue or DQ, the first descriptor always valid. So the process for this very first descriptor always get a simple logic, and we can do some kind of parallel processing. On the other hand, let's see flow extraction, if that's suitable for you to using this technique. The flow extraction is quite different, since any single packet might be different at the very beginning of a flow extraction process. Let's say a packet might have VLAN header or have different kind of Ether header. So there are a bunch of branches in that piece of logic. So it's really hard to parallel that kind of logic. Here's a load balance. It's pretty important in my mind. So take a concrete example. Let's say in a system we have, let's take an example of NFV type workloads. We have, if we have one RxQ, physically RxQ and one virtual RxQ. And we have two polling threads. If we happen to put those two RxQ on the same polling thread, what will happen? We can only get almost half of the overall peak performance you can get. So that will be very significant to really have an effective load balancer. The load balancer will essentially do two things. One thing is that when a new RxQ comes in, you need to place it on the least load thread. And the second thing is that this should scheduling most busy RxQ to the least busy thread. So that's the two most things you need to be done. Here loads just calculated from the sampling of CPU usage, but it will be great if we can take some pseudo metrics, let's see, number of RxQ for a particular thread. So, but anyway, the load balancer is significant. Adaptive polling, that essentially means efficiency. So, as we just mentioned, virtual switch is in a very, very unique position that CPU efficiency is super, super critical. So we need to think about this very seriously. The busy polling, like the basic DPDK model, just pure polling, as we know that it's very bad for lightweight traffic. So even there's no any single packet comes in, you're still using 100% of a CPU core. And DPDK right now probably support, I didn't really follow up on this, but it seems that the user space interrupt plus plus polling is working, but I don't think that's good enough. So we need an adaptive interrupt plus polling. And the thing here is that it's unnecessary to provide an adaptive polling mechanism to ensure the CPU usage is perfectly linear to the workloads. But the bottom line is that for heavy workloads, those kind of mechanisms need to have a performance on par with pure polling. So the design philosophy is that for heavy workload, we try to keep this same kind of performance. But for other less lightweight workload, we try to improve the efficiency. That's the whole idea. For efficiency, another thing is about packet group metadata. I guess you guys probably never heard about that, since it's not in DPDK or OS. So the idea is that sometimes
our design philosophy is that we try to use a virtual switch to support both very high throughput workload and also very feature richness workload. So for NFV type of workloads, we don't want to lose too much overhead in our case. So if we can associate some kind of metadata for NFV type of workloads, in the middle, we have a complexity logic or feature set. We can easily skip that piece of logic instead of inspect some fields for each individual packet. The whole idea is so it's really expensive even we inspect a single bit of each individual packet. So in this case, we can skip the whole vector of packets as a whole. This is for packet copy. I think that will be pretty straightforward, as Huawei already mentioned it on the previous talk. I think that set a good context. And essentially, in normal case, we have a few memory copy. And if we're using TX0 copy, we can save one copy at least. But one thing I want to mention here is that we need to have a much more sophisticated, here I mean down, this notification mechanism to free the vhost ring resource, ring buffer resource. So let's take an example. If a unbuff happens to be Q in case of cost, so you need to do something different instead of hold on the volatile unbuff. So you need to really think about that. Another thing is from security perspective. Let's say a packet comes in and we have done the forwarding DC. So that it's on the path to the destination port. But here's a malicious guest. Just try to change the packet content. That would be horrible. So you need to really think the delay copy is good, but we need to consider the security issue here. So the solution will be you need to ensure a reasonable length of headers cannot be changed by a guest over the whole cycle when it flows through the whole virtual switch. Okay, just talk about something about the performance and the efficiency. And here is about the extensibility. As our goal is try to have a unified architecture to support a variety of workloads. So extensibility is super important. Here we just have a LED chain framework. It's pretty kind of, it might be kind of like a graph node in FDIO. And but it's RCU protected. That means every change on a single chain cannot really impact the whole performance of the data path. And obviously, that chain can leverage the packet group metadata we just mentioned to easily skip a few that chain features. Secure group, that will be an interesting topic. Probably not for DPDK team, but probably for OS team. And for now, CloudNetEngine virtual switch just using BFP. That's a firewall on NetBSD with Jet engine. That means it's not running BFP bytecode state machine. Instead, it just translates into the native CPU instruction. So it's have a pretty good performance. And this technique can really support to match arbitrary fields of a packet. And it's very like a Linux NF table, as we know. Here is things that, as we know, that the OS team is also doing some work on secure group. They are using collection track plus recirculation to support a secure group. But theoretically, that will introduce one more flow lookup. So let's see. At first, when a packet comes in, it match a full flow. See, hey, I need some states matching. You go to the collection track. Then collection track will recirculate. That means re-inject the packet back to the virtual switch core. And this packet will go through the whole flow lookup again. So that have two flow lookups. So in your opinion, that's might be introduced some overhead here, but we think that performance data can tell which one is better. So let's see what will happen. Overlay. Everyone dealing with public cloud must have a very solid overlay solution. So when we provide overlay solution on user land, there are a couple of things we need to think about. So two major parts is routing table and the up table. So in that sense, there are quite a few work we can leverage Linux kernel. So it's unnecessary to really maintain the whole routing protocol in a virtual switch. We can really think up with a kernel. So that means any routing protocol or SPF can set up on the hypervisor, and we can just dynamically sync up those kernel routing table to our user land. But for ARP table, that might be different since there have some tweaks. And so we might just intercept all of them, just absorb the incoming ARP packets. So we cannot fully use kernel ARP table since you're going to be timeout. There's no subsequent ARP requests coming. But definitely, we don't need to build everything from scratch. Here's an interesting thing about the tunnel acceleration. I guess you guys probably never heard it before. And so the idea here is that when we look at that typical deployment in cloud environment, we can find that there are a bunch of tunnels are essentially sitting between a pair of labels. Here I mean labels, that means they're sitting on the same layer to broadcast domain. So in that case, it's unnecessary to use IP or UDP encapsulation to really deliver the inner payload. We can essentially just using the mic layer to encapsulate the inner payload. So that's the whole idea here. But it needs in an adaptive way. That means this layer 2 encapsulation and the layer 3 encapsulation actually working together. So you need to find, let's say if the tunnel is just across a router, in that case you have to use in the IP or UDP encapsulation. But if you find that's layer 2 adjacent, you definitely can use this techniques. And for instance, take the 64 bytes payload as an example. In typical VXLAN, if we're using typical VXLAN encapsulation, we can only have 56% utilization rate. But when we're using this acceleration, you can over 64%. Oh, sorry, 74%. In last presentation, there are some engineers asking the question about offloading. And right now, the DPDK community's solution is just say, hey, when a TSO packet from a VM needs to forward to another VM on a single host, it just flip a flag and let it go into the VM. That's the community doing. Here, what we are doing is very different. So we providing essentially the software offloading. So in that case, it's totally transparent to the guest VM. You don't need to really bump up the MTU setting for VMs. So, but there are a number of cases. So doing offloading correctly is not an easy job. And we can see there are different cases. The first two cases are actually for native traffic. That means there is no overlay involved. So VM for VM, even we're using overlay, essentially there is no encapsulation as they are on the same host. So in that case, we're just using native software offloading. And for VM to PNIC, we're just using native hardware offloading. That means we can, for those kind of workload, essentially just provide the correct information to the hardware, then hardware will do this for us. The last two is really about the offloading. One engineer from uCloud just asked the question, if we happen to have a kind of encapsulation, but the hardware don't understand this encapsulating format, how could you do offloading for this case? So here is the answer. Actually, we do, if the NIC don't really support this over the encapsulation format, we're just doing in software. So you need to do it very, that's a little bit, there's going to be some tricks. So since you TSO native packet, and when you TSO overlay packet, that's a little bit different. So you must carefully dealing with this. Sleeving, also some guys asked this question. It's pretty important. So there might be a bunch of troubleshooting, automatic troubleshooting tools available from SDN providers. Let's say some trace flow or something. They can nail down the problem. So if the point A to point B, there's some problem, it can nail down to some entities in the middle. But when you try to troubleshooting where is the exact problem on that particular entity, you need some definitive tools. Probably in that case, a TCP dump will be the most often used tool everyone going to troubleshoot your networking. And so we provide a TCP dump interface to really dump all of to sleeving all of the packet for any interface for both physical networking and also the virtual ports. Okay, that's the detail sharing. And here is going to be some performance data. But the performance data is not exhaustive, and the setup is not the latest, but I just try to give you a sense. Here's an NF type of workload. It's pretty simple, and on the left side there is a test target. It's a VM running with L240. And the right hand is just the packet generator. So essentially just the airping and traffic through this VM. And the hardware configuration, I will not mention, you can take a look offline. And the OS, we're just using 2.4. For native kernel OS, we're using 2.4. And for OS DPDK, it's OS 2.4 plus DPDK v2. And for singing virtual switch, we're just using we have a technical preview, and it's technical preview update 4. So here is the data. As we can see that for package size 256, 6 bytes, saying virtual switch get 10 gig line rate on that particular setup. And in that case, OVS DPDK probably 60% overall throughput. And for 512 bytes, we can see that saying virtual switch, you get a higher throughput in the less CPU consumption in that particular case. And so that's the NFV workloads. In that case, kernel OS probably we can just ignore since it's much, much worse than the other tools. Anyway, this is best case for OS DPDK, I think. And we just show our data comparing to OS DPDK. And the next performance comparison is about for traditional enterprise workload. We don't using packet generator to inject different kind of different size of small packet. Here we're just using iPerf to generate a bunch of TCP flows. And over that TCP flow, they're going to send a bulk data. So the configuration, the software and the hardware configuration is exactly the same as the NFV workload. Only the testing driver is different. Here we're just using 2 VM to drive the test. As you can see, in that case, OS DPDK probably the worst one. Why that happen? Because it doesn't really support software offloading perfectly. And in that case, we can see when CloudNetEngine virtual switch compared to kernel OS, we pretty much get maybe 50% better than kernel OS from throughput perspective. And the right hand, it's the CPU consumption. You can see CloudNetEngine virtual switch probably only half of the CPU usage in that case. So if you have a quick calculation, it pretty much means we have 3 times better than OS kernel data path. That's super, super important, as I mentioned before, since since virtual switch needs to be running on the hypervisor to share the computing resource with other VMs. So if we normalize the packet, the throughput to 10 gig or to 12 gig, we can see on that particular setup, we can essentially save more than 1 core. That's super, super significant. So hope you can get an idea on the performance data. But as I mentioned, it's not exhaustive, but just some very typical cases for NFV and enterprise workload. And but the test is not using the latest software yet, but we'll try to put some effort to rebase to the latest code to test it again. Okay, I'm going to take question.
喂。
我用中文吗？我用中文好了。OK， 我是来自英特尔的，然后我也是做 DPDK 相关的一些测试。其实我测过这些相关的一些性能吧，就 DPDK 加 OVS 可能和您的测试结果有一些出入吧。我的结果可能比这边你展示出来的会好一些， 所以我不知道就是你的一些具体的一些配置上是没有优化呢，还是因为比如说像这个VM to VM 的话，都是用Legacy 的 virtualnet 就 kernel 的 virtual， 再加上 DPDK 的 vhost， 就是我们的性能可能会比你这边的好很多。
Okay. You mean the question was about
performance difference.
Okay.
Test result is different from you.
I try to understand the difference is just a relative difference or is absolute. So since we just using the hardware is pretty
similar.
down. Yeah, well, I mean maybe not powerful as what you are using. So the absolute number might be different. You mean you are using the same kind of hardware setup?
Very similar. Since V3 is hash wheel server and NIC is Niantic, 10 gig, and 6 you are using 6 physical core. 你是用6个 physical core， 然后12个 logic core.
No, that's just the configuration. But
okay.
usually in the test we're just using one single core for virtual switch.
Okay, so for the Qmio 你有用什么 core 吗？你有用 task set?
No. So for VM and QEMU, we don't do any banding. So there's no any affinity. Yeah, all the tests we just don't use any affinity, and the hyper-threading just enabled. So the hardware, software just using the default one.
Okay. 因为我觉得这边 virtualnet 在 VM 里面，因为是 kernel 的，它其实跟 core 的绑定关系倒不是特别大。当然 task set 的话会提高一些性能，但就是说我看到的性能 gap 可能是比较大的，可能是有几倍的性能差别，不是说对，所以 TSO 你在这里有支持吗？就是说因为 TSO 可能没有支持，因为这是 2.0 的版本 DPDK。如果是用更新的 DPDK 的话 ，2.2 以后应该是，或者是16.04的话，应该会支持。就是说，这个性能我觉得应该会有个很大的提升。
Yeah. As you know that I just mentioned that we're using very different TSO technique here comparing to DPDK. What is doing in DPDK?
Thanks to Xiaojun's startup and all of these new ideas, but time is over now. Let's spend more time and communicate together. Indeed, Intel publishes some data and you publish some data, so we can do more comparison in future. Thank you, Xiaojun.